This is part 2 of our neutralization series. We're going to see how we titrate an acid or base, and we're going to look at the apparatus and how we use it. In the flask down here, called an Erlenmeyer flask, we would place a solution of known volume and unknown molarity/normality. The stopcock here will control the flow of the titrant into the flask, and we'll typically use a 50 milliliter volume burette. We clamp it so that it doesn't fall during the titration. In the burette we place a titrant, and typically this is going to be a known molarity or normality solution of the opposite of what's in the flask. And we'll have in the flask an indicator. The one for this one would probably be phenolphthalein. We're going to assume that a strong or weak acid is in the flask and that we want its concentration. And if we did that, we would titrate with a strong base, typically sodium hydroxide. And as I said, the phenolphthalein is our indicator. It'll change colors as soon as we add one drop past the equivalence point. Let's start off without any sodium hydroxide, just the acid in the flask. And stage 0, we're going to put 0.01 molar hydrochloric acid in the flask. We're going to add exactly 25.00 milliliters, plus or minus 1/100 of a milliliter. And in the burette, we're going to have 0.01 molar sodium hydroxide. That makes the math easier. We obviously have a pH of 2. Follow along with your calculator in these molarities and pH calculations. Since there are 0.25 millimoles of hydrochloric acid in the flask, we can begin. In stage 1, we're going to add 10 milliliters of the sodium hydroxide solution. Multiply volume times molarity, we get 0.1 millimoles of the base, which will neutralize 0.1 millimoles of the acid. That'll leave 0.25 minus 0.1 millimoles of acid, or 0.15 millimoles of hydrochloric acid. Fully dissociated, so the volume is 35 milliliters. We divide 0.15 by 35, and we get a concentration of 0.0043 molar HCl. We punch in for the pH, and we get 2.37, and we have graphed that here. It's only nudged the pH up by 37 basis points. In stage 2, we're going to add another 10 milliliters of the sodium hydroxide, same number of millimoles, neutralizes the same amount of hydrochloric acid, leaving behind now 0.05 millimoles of hydrochloric acid in the flask. The volume is now 45 milliliters. We divide 0.05 by 45, and we get 0.0011 molar. We've still just edged up a little bit. The pH is now not even 3, 2.95. Now in stage 2.9, we're going to add 4 milliliters of the base. That's 0.04 millimoles. It'll neutralize 0.04 millimoles of HCl. We now have only 0.01 millimoles of HCl down in the flask. The volume is now 49 milliliters. We divide millimoles by milliliters, and we get the concentration of 0.2 molar and 3.69 pH. We are not even to 4, and we've added almost enough to totally neutralize. We've just got 0.01 millimoles in the flask, but we're still at a pH below 4. Now we go to the equivalence point. We call it end point because the indicator is probably going to change colors right about the same time. We add 1 milliliter. That gives us our last 0.01 millimoles of sodium hydroxide. It neutralizes the last of the acid, leaving no acid. The volume is 50 milliliters, but now we have nothing but sodium chloride solution in the flask. There's no excess acid or base. The end product is a neutral salt. It doesn't hydrolyze, so the pH must be 7. Unless, of course, we've got some carbon dioxide from the air in there that would lower the pH. But let's just assume we have no carbon dioxide around. The pH is 7. At stage 3.1, we're going to add another milliliter to get us the same distance passed as 2.9 stage. When we do that, we only have sodium hydroxide in the flask, 0.01 millimoles. We divide by the 51 milliliter volume, and we now have 0.002 molar hydroxide. We punch that in, we get the pOH, 3.71. We're going to subtract that from 14 to get the pH of 10.29. You can see that in just a matter of 2 milliliters, we've gone from a pH just short of 4 to a pH that's a little bit beyond 10. That's about 6 pH units in 2 milliliters. Now we're going to add excess base. With a total of 45 milliliters of base, there's no more acid to neutralize, so we've got 0.05 millimoles of sodium hydroxide and 55 milliliters of volume. The concentration is 0.05 over 55. The pOH is 3.04, and we subtract from 14 to get a pH of not quite 11. As you can see, it's starting to bend over here with this negative curvature. We add another aliquot of base to get up to 40. There's no acid. We now have 0.15 millimoles of sodium hydroxide and 65 milliliters of solution. The pOH is 2.64, the pOH 11.36. And finally, stage 6, we add another 10 milliliters of the 0.01 molar base. Again, there's nothing to neutralize, so we have 0.25 millimoles of sodium hydroxide in the flask. But we have a larger volume, 75 milliliters. The pH is 11.52. You can see here towards the end we have something very much like a straight line. Here at the beginning we had something a little more like a straight line. But we have this wild increase here and then the leveling off there. This gives you a picture of the titration curve with the points that we have plotted. We noted the rapid change in pH here before and after the equivalence point. So we've explained how the pH can make such a wildly vehement increase right around the equivalence point of the titration. We should therefore change colors of indicator at or just past the pH of 7. And we will learn in AP what we mean by pKa. Every indicator has a pKa, and it should change colors. We should have an indicator that changes colors just about the pKa of the salt that is formed in the neutralization. In this case, the pKa of sodium chloride would be 7. So we would choose phenolphthalein because it changes colors just a little above 7, from a colorless to a nice bright pink. And so phenolphthalein would be our indicator of choice. I think thymol blue might also work. But methyl orange that changes colors down here will not.